Welcome. In this video I'm going to talk about the idea of moment generating functions. So the moment generating function is something that is associated to a random variable. So if we're given x, a random variable, then we're going to produce from that a function of some new kind of dummy variable t called its moment generating function. What we're going to see is that this moment generating function is going to be a kind of an alternate way of encoding information about our original random variable. When it exists, it typically will exist, it will contain all the information that the original random variable contained, and also be amenable to extracting interesting bits of that information in nice ways. So first off, how is this thing defined? Well, just the definition is that this is the expected value of the expression e to the tx. So let's think about what that means. If I were to give you any particular value of t, for example t equals 2, then you can consider the new random variable e to the 2x, some new random variable derived from the original one. And of course it has some expectation, some expected value, which is a number. If I were to give some other value for t, I get some other random variable and I can calculate its expectation, etc. In this way, given any t value, you get some number for this expected value, and altogether this function of t, or written symbolically like this, is what we call the moment generating function. Okay, let's make this a little bit even more concrete. So, of course, the random variables that we're going to consider two basic flavors. Flavor number one is that x might be a continuous random variable with probability density function some f of x, or it might be a discrete random variable with probability mass function some p of x. So, of course, in these two different cases, we have different explicit ways of writing down what expected value is. So what is this equal to? Well, in the continuous case, this is the integral of the expression that we're looking at with x plugged in, substituted for capital X, times the density function dx. This is the continuous case. And in the discrete case, we're going to take a sum over all the possible values, the discrete values that x can take, of this same expression, e to the tx times the density function p of x. So concretely, this is what we're talking about. You give me some particular value of t, you can do this integral, or you can just do it by leaving t symbolically alone, etc. And the value that you get as a function of t is the moment generating function. Before we go further, it makes sense to ask the question, why are we considering moment generating functions? What's so nice about this kind of an expression? Well, perhaps it's not a surprise that these are useful things to calculate moments of random variables. So that is to say, these give us a nice way of computing the expected value of x, or the expected value of x squared, or more generally, the expected value of any power of x. To see how this works, let's consider taking derivatives of the moment generating function. It turns out that if you take the derivative with respect to t of this thing, then interpreting that on the right, you can actually bring this derivative on the inside. So I'm not going to fully justify that now, but in fact, you can bring this derivative on the inside. X we think of as a constant in this context, And so this is actually x e to the tx is the derivative of this expression. Let me just call this m prime of t. And now, if you were to plug in 0 and consider m prime x of 0, that's going to be the expected value of this thing where t is plugged in to be 0, but that's just of x. Okay? So we quickly see that you can get the expected value by taking the derivative of the moment generating function and plugging in 0. Similarly, you can take higher derivatives. So you can see that if you take, let's say, the nth derivative of the moment generating function, well, what is that? That's going to be the, by this same kind of trick, the expected value of the nth derivative of e to the tx. Each time you take a derivative of that, x again is just this constant, it's going to pull down in front, and you're going to get x to the n e to the tx. If you were then to plug in 0, you would get the expected value of x to the n. Okay? So these moment generating functions are really nice in that they encode in an easy to read information about expected values of powers, which then give us nice shortcuts to compute means and variances and such things. Alright, so if you'll allow me a little grammatical liberty there, I want to say just a few words about how these moment generating functions are able to contain the same information as the original function. I'm just going to give a few words about this just as a kind of motivation. So let's consider the continuous case, for example. So in that case, the moment generating function, the expected value of e to the tx, is given as the integral of the expression e to the tx times my probability density function, dx. And the way to see that this contains the original information is to make a substitution and consider the moment generating function of I times t, the imaginary number I. What you then have of I tx, f of x dx, or maybe to be a little more standard even, I will do the moment generating function of 2 pi it. And then you see what you have here is actually the Fourier transform of the probability density function. So, if you've seen Fourier theory, then what you know is that the original function is going to be determined by its Fourier transform by doing the Fourier transform again and dividing out by the constant that comes out in front. So, because a function is determined by its Fourier transform, the original function, the original density function, is determined by its moment generating function.